So today's topic is subspaces of vector spaces. And subspaces are a general theme in math. In fact, I would go as far as to say that whenever you're doing any kind of algebra, if you have some kind of mathematical object, then you'll be interested to know what sort of objects there are inside that object that have a lot of the same structure. In other words, what are the building blocks? So, without any further ado, we have the definition. If you have V a vector space, then a subset U is called a subspace of V if you want to be specific. If U is also a vector space with the same addition, scalar multiplication, identities. I think that's everything, the identities. Yeah, that seems like everything. We have a slightly, I don't know if I should call this a proposition or a reformulation, which says U is a subspace if and only if U contains the zero vector, U is closed under addition, and then lastly, it's closed under scalar multiplication. So if U is in U and A belongs to whatever the field is, then AU in U. Okay, as always with this, we should think a little bit about what it is that this is asking us to check. And then I'm going to promptly not check it and let you read it because, properly speaking, it's a little bit tedious to go through this, right? To be a subspace means that you're also a vector space. And so to really give a completely airtight proof of this, one has to go through and check all of those axioms with the, when you equip that subset with these operations. On the other hand, well, this should in a sense be a little bit straightforward. Because, for example, let's just think about one direction. The easier of the two directions hopefully gives some intuition. If U is a subspace of V, then in particular, the original definition says that it's also a vector space, so it has an identity. And I already said you have to have the same zero and the same addition and the same scalar multiplication. So, in other words, because we know how those things work in the big space, all this is saying is that you are a vector space within the vector space. So the vector space axioms should all be kind of close to free. They should come from just how we know how V works. It's just that there's a lot of those things to check. And so a lot of trivial things to check means I skip checking them. That's how it works. Let's see examples, because I think this is much more useful of a way to spend our time in this video. Axler gives a bunch. Let's start with the first one. I think that one is arguably the most important. Let's say we look at a set of quadruples, x1, x2, x3, x4, where all of our xi's, oops, sorry about that. I must have touched something. Go away, please. Let's put this in F4. And then we insist that x3 equals 5x4 plus a number b. Axler tells us that this is a subspace of F4 if and only if b equals 0. This is a general principle of linear algebra, so I want to take a moment and talk through this, hopefully in a way that convinces you that it's true. So if x3 is equal to 5x4 plus a constant, right? In other words, the information about what's in x3 is kind of not important in the sense that I know x3 once I know x4. The question is, are we going to satisfy these three requirements according to the proposition? So first off, let's consider the reverse direction. In other words, let's assume b equals 0. Let's check that the three things are true. So the 0 vector of f4 is the vector 0, 0, 0, 0 in f4. Of course, that satisfies this because x3, 0, equals 5 times x4 plus 0. So this condition is satisfied. What about condition 2? If I have two such vectors obeying this rule, then their sum does. So let's see. If I have x1, x2, x3, x4, y1, y2, y3, y4, I can add these together. We know how addition works when I'm working over a field, I just add these things. I get x1 plus y1, x2 plus y2, x3 plus y3, x4 plus y4. Now, the rule is the third coordinate has to equal 5 times the fourth coordinate. So in other words, is it true that x3 plus y3 equals 5 x4 plus y4? The answer is yes, because the distributive property gets me this thing. And I know that x3 is equal to 5x4, right? This one pairs up with this one, and this one pairs up with this one. So this equation is still true. Lastly, I have to see that it remains true if I do scalar multiplication. So if I just take, let's use a new letter, z1, z2, z3, z4, and I multiply this by some a, we know this has the effect of multiplying every entry. And now, is it still true that the thing in the third coordinate is equal to 5 times the thing in the fourth coordinate? And the answer is yes. By just using our axioms to multiply this and then use commutativity and then pop it back out again, I can cancel this from both sides and see since z3 is equal to 5z4, a times z3 is equal to a times 5 of z4. And so we checked it. Right, that gets the third condition. What about the forward direction? In other words, if I know this is a subspace, what should we call this? I didn't give this set a name. How about we call this just S for set? So now I'm assuming S is a subspace. I need to prove that B is equal to 0. Well, instead, we do a little logical trick, namely the contrapositive. I prove that if B is not 0, S is not a subspace. And for that, we just look at the very first condition, namely, all the conditions fail, but let's think about the first condition. If x3 is equal to 5x4 plus a constant, and that constant's not 0, what's up with the 0 vector, right? Is the 0 vector even in this list? No, it's not, because this thing does not satisfy this equation. If I try to plug in 0 and 0 respectively, I get 0 equals b. And so this thing would not even be in S in that situation. Okay, let's press on. Let's try to see at least one other example, and then maybe we'll break this video up because it's we don't want to have it get too long. Let's talk about one of the examples that I mentioned last time, namely the set of complex sequences which converge to 0. This is also a subspace, and let's check it. Again, using the proposition. The first requirement is that the 0 vector be in the set. Well, what is the 0 of this set of sequences? The 0 is the 0 sequence, or more specifically, Zn equals 0 for all n. Of course, if Zn is already constant, then this limit is 0, right? How could it not be? It's already constant. Next, we have to show that if Zn and Wn are both sequences whose limit is 0, then I can take the limit of their sum and also get 0. Well, we know from our calculus days that since the limits exist individually, that I can break it up and get 0. And lastly, if I have a sequence which converges to 0, is it the case that AZn for any complex number A will also have limit 0? Of course, because we also know that, again, when limits exist, you can pass constants through them, and any complex number times 0 is 0. Okay, how long have we been going for now? Almost 12 minutes. I think this is a good place to stop for this video. We'll break this one in half. There's one more sort of topic in this vein that we should take a look at, but I think these examples are enough to warrant a natural breakpoint. See you in a sec.